Okay, good afternoon, everyone. Let's get started. Okay, hope everyone enjoys the spring. It's getting warmer and warmer and green. First up, I want to answer some questions I received while email or Canvas about final exam. Again, the final exam will be taken in person in this classroom. So we're not asking everyone to join every lecture, but the final exam, please do not miss it. Otherwise, you're gonna miss 20% of credits on your final grade. That's not good. And second, someone asked if there are gonna be some mock exam. We'll have some like a final exam practice. I'm not sure, according to the progress of our course, we're gonna hold a mock exam in class. That might not be necessary, but we'll definitely share with you some like exemplar final exam paper, and you can take a look and do some practice if you want. And I will also share with the answer case, so you can take a look. That sound good? Any question? Okay. Yeah, the second thing is about quiz 8. Some students complain to that some problems they have met have never been covered. And I did some check. I found out, okay, the problem indeed contains some problems which are covered until this week. So we decided to not to have any quiz this week. So if you want to retake quiz 8, just send us an email. So we're gonna give you more attempt, but we have definitely checked every problem, I mean the problem library, because the problem just pop up randomly. If you want to retake it, if you you feel like because this week the things we discussed this week will definitely cover every possible problem in quiz 8. So if you do want to take it again, just shoot us a message in Canvas or email by Thursday, so that we can arrange the quiz 8 again and say make you are able to retake it by Friday. But if you have already got 100 points, then there's no need. I mean, it's up to you. Like if you feel like, okay, because the instructor has not yet covered some topic which causing you getting some point detected, you want to retake, just let us know. We'll make an announcement on Canvas later today. Okay, any question? Great. So for heads up, we have released homework 5 today, but of course homework 4 is due today, and hope everyone won't have some like late penalty on that. And technically speaking, we'll only have 2 more assignments, homework 5 and homework 6, and then we need to schedule the final exam. That's the only remaining workload for this class. Again, because the semester end is approaching, I believe many of you need to prepare a lot of, maybe not a lot, but quite a few final exams, project report, and all those kind of stuff. So please try to allocate your time and seek for help in time. And again, our office hours is open every week, every weekday. So we'll be happy to help you with it. Any question? Okay, perfect. So let us continue. We're gonna first wrap up the joint continuous random variables. Then we will proceed to covariance, correlation, and correlation coefficient definition. Okay. So we know that if we got 2 random variables, x and y, which are continuous random variables, then we can define a joint probability density function, abbreviated as joint PDF, right? And based on the joint PDF, oh, by the way, I'm gonna just please bear with me. I'm gonna repeat the definition. So we require the joint PDF is always non-negative. And if you integrate, now you have to do some double integration, right? Because you got two random variables. If you integrate the joint PDF function over the entire domain, it should be 1. And if you want to calculate the joint probability of the events like X belongs to a range A and B, meanwhile, Y belongs to another range C and D, this type of event, its probability can be computed directly by integrating the joint PDF across this across these two intervals. That's the definition of the joint PDF. So it's a direct generalization of the PDF for a single random variable. And then from the joint probability density function, we can get the marginal probability density function for a single variable. How can we get it? Yeah. Exactly, right? That's how we get that's how we do the so-called marginalization. Right? So if we want to get the PDF for a single variable X, what we need to do is that, okay, we're going to integrate the joint density, but the integration is only over Y. Similarly, if we want to get the PDF for the random variable Y, you're gonna integrate the joint density function with X only. So you're gonna treat Y as a constant, right? So just keep in mind that whichever variables marginal PDF you want to get, you're gonna integrate with all the other variables. Right? That's how we do this so-called marginalization. Any question? Okay, so and based on the joint PDF and marginal PDF, we define a so-called independence, right? So we claim that two continuous random variables, X and Y, are independent if and only if any of these three conditions hold. So this is very similar to the cases we talk about for discrete random variables or for random events. If the joint density function can be decomposed as the product of the individual probability density functions, fxy can be written as fx times fy, then we'll claim x and y are independent to each other. And this one is also equivalent to the conditional probability density function of x conditioned on y equals to the marginal density function for x. Symmetrically, the conditional probability density function of y conditioned on x is equal to the marginal density function for y. Okay, so these three conditions are equivalent to each other. And also, oh, by the way, we need to make sure that the equality must hold for every possible x and y values. It's not just for a special choice of x-y pair. It must hold for every possible x-y pairs. If that's the case, then we claim that x and y are independent to each other. Intuitively, these two conditions might be more reasonable. These two are just saying that, okay, if you look at the PDF for a variable, you find that its density function doesn't change at all, no matter it is conditioned on the random variable y or not, right? So that basically implies x and y are independent to each other. Right? Similarly, the PDF for y doesn't change if you are conditional on x or not. Then that basically means, okay, the density function of f, density function for x has nothing to do with y. So x, y should be independent to each other. Okay, any question? Okay, great. So also did some like examples last lecture. We're not gonna repeat that. So a very important definition is called conditional expectation. If we want to look at what is the expectation of a random variable x, conditioned on that you observe the random variable y takes some particular value, small y. This is called conditional expectation because you have some conditional, parts or conditional observations, right? It is conditioned on you say some other things happen. Here it will be, okay, you say the random variable big Y takes some value, small y, right? So the calculation of the conditional expectation is very similar to the normal expectation. The only difference is that you're going to replace the density function from the marginal density to the conditional density. Okay? So if we calculate x, expectation of x, right, condition on nothing. So from our previous discussion, right, we have discussed about this a lot. So we're going to just integrate x multiplying with the marginal density of x, right? You just do this integration over the entire domain that x can take values. So this is the expectation of x, how you're going to calculate that, right? But now if we want to compute the conditional expectation, right, then you're going to replace the density function with the conditional density. That's the only difference. So now I want to ask, after I calculate this conditional expectation, does this value depend on x anymore? Any thought? If I just calculate this guy, right? Following the formula here, does the value count on x anymore? No. Why? Yes, exactly right. It is integrated out, right? All possible x values have already been integrated in calculating the final result, right? So it is constant x. But is this conditional expectation irrelevant to anything? Is there any other variable this conditional expectation related to or depend on? If so, which variable it depends on? Why? Why? Why it depends on y? Yeah. Yeah, exactly. Right. Combine your thought and their thought. That's a perfect explanation. So this is a very, very important um, concept or insight. Please keep it in mind. So basically, you can view this conditional expectation as some function of y. Why? Because when you choose different value of y, imagine you're going to have different conditional expectation value, right? If you take y equals to 1, then your conditional probability density function might be some kind of function, right? However, if you vary y to 2, your conditional density function might change, and so is the integration. So that means, in general, this conditional expectation is constant to x, but depends on y. It should be viewed as a function of y. Any question? Great. So now let us look at one concrete example, which we have not get time to finish. Okay? So suppose this is our joint probability density function, PDF, right? This example we have seen before, but we didn't write the domain here. But here we should supplement domain. So x belongs to 0, 1, y belongs to 0, 1. So now, based on this joint probability density, we want to compute the conditional expectation of x conditioned on y equals to half. How can we calculate this? How can we obtain this conditional expectation? Any thought? Yeah. Yeah, that's the first step. And do you have additional steps? Mhm. Yeah, yeah. So from the definition, we actually need to figure out what is the conditional density function for x, condition on that y takes some specific value, half here, right? So of course, if you want to compute the conditional density, you're going to leverage the joint density and marginal density, right? So what you said, part 1 is definitely correct. And part 2 is that, okay, we need to divide this joint density by the marginal density, right, to obtain the conditional density. So in detail, let's first write down the conditional density according to the definition. That means we're going to divide the joint density, which we're going to take a particular value, right? And then, yeah, maybe I should. And divide it by the marginal density of y, right? But here, y, you're gonna take the particular value you are conditioned on, right, which is half. Does it make sense? right? So now let us we have the joint density here, x squared plus 4/3 xy plus y squared, right? So the numerator is pretty straightforward. What we need to do is that, okay, you're going to replace y by half. Then the remaining thing is that how do we identify the denominator? The denominator is the marginal density function for y. You're going to evaluate this marginal density function at half. So let's do it, right? So we want to calculate the marginal density for y according to what we just have discussed. We're gonna integrate the whole joint density function with x, right? You just need to integrate all the other variables in your joint density function. So that means I'm gonna do a integration over the joint density over x because I want to get 1. And x is in the domain 0, 1, so I don't need to put minus infinity to infinity, I just put 0, 1. And now we just substitute the true form for fxy and calculate that, okay? So this one would be, let me do this, 0, 1. I'm gonna just write down fxy, x squared plus 4/3 xy plus y squared dx, right? So you see that we can just, integration of sum is sum of integrations, right? So just to do it one by one, but here 1k point we should be aware is that doing this integration, we need to treat y as constant. Nothing to do with x, right? We treat y as constant, and then it's fairly easy to show that, okay, integration with x squared is what? 1/3, right? It's 1/3 x cubic 0, 1, right? This first term. How about second term? Any thought? Yeah. 2/3 x squared. Yeah, 2/3 y x squared, right? And you're gonna evaluate at 1, 0, right? Okay. How about third one? What's the integration of with respect to x for y squared? Y is y squared x. Yeah, but here, yeah. So here, remember, y and y squared are constant to x, right? So you're essentially integrating. You can take x y squared outside, right? So you can just, oh, sorry. You can just do 0, 1 times 1, right? So this guy actually is just 1, right? Does it make sense, right? Because the constant function, if you integrate that, it's just the range, the length of the range, right? Okay. So this one is 1. So now we can get our marginal density function for y as 1/3 plus 2/3y plus y squared, right? So now the conditional density is simply x squared plus, you're gonna, numerator is just a joint density function just the copy function here. And the denominator is the marginal density function of y, right? Now, we specifically take the value of y to be half. So we're going to evaluate at y equals to half, right? That will get your conditional density function of x when y takes the particular value half. Any question? Okay, so if we write it in a fancier way, it will be like this, right? If you just substitute half for y in the denominator, it will give this fraction, 11 over 12. And in the denominator, we're gonna replace y by half. It will give x squared plus, you see this 4 over 3 times x times half, right? So it will with 2 remaining in the denominator. So it's 2 over 3x plus 1/4. Okay. So then you get your conditional density function of x given y equals half. Then you just integrate. Remember, we're doing conditional expectation, right? You're going to integrate x multiplying with this conditional density function of x. And the remaining calculation is quite tedious. It's still doing some kind of like integration, but now it's integrate along with x as well, right? So eventually it will give you the number here. Any question? Everyone feels comfortable? I mean, we highly recommend everyone to practice this, right? Because this is only the practice will help us understand or memorize those definition concept. Okay, so one more in-class exercise is like this. Let us consider two dice rolls. You can view it as I'm gonna roll a dice for twice and independently, meaning that for each die you see any point with the chance 1/6, right? Is equally. Or you can view it like you roll two dice jointly, but for any pair of the points you see has the equal probability, which is 1/36, right? I mean, you can view this, you can take the two views like equivalent. There's nothing different. Okay. And then we want to look at the conditional expectation. What is that conditional expectation? We want to look at the expected value of the sum given that the first die was 3. Right. So let me, for better illustration, right? Let me draw two dice, right? And you got equal chance to see every point, right? So let me denote the point you see from the first die is x, right? The point you see from the second die is y, right? But here we want to look at their sum. So let us define a third random variable, z, which is simply x plus y. Okay. So the conditional expectation can be written as what's the expectation of z, right? Condition on that, the first die was a 3, that means the condition on x equals to 3, right? That is our problem. Any question? Everyone feels good? This is how we mathematically describe this problem. Okay, then the question is, how do we calculate this conditional expectation? How should we do this? How should we solve this problem? Any thought? Yeah. Mm-hmm. Yeah, that's a good idea. Yeah. Okay, so let me summarize and extend what you said. Okay. First, we're going to start with the definition, right? We always start from definition. The conditional expectation, according to the definition, will always be some kind of integration z times the conditional density, right? Conditional density of z given x takes the value of 3, right? And you're going to integrate with z, right? Here, remember x and z are discrete random variables, right? So actually, we do not need to do integration. We're just doing summation. So basically, it will take all possible values that z can take times, so let me see k, right? K is every possible value z can take. Takes z times the conditional density of z taking that particular value condition that condition on x takes value 3, right? So that's how we're gonna calculate this conditional expectation. Do we agree? Right? Any question? Everyone is happy with our current state, right? Okay, so then the remaining thing would be, okay, how do we identify the conditional probability density function, right? In the discrete random variable case, we probably also call it conditional probability mass function, but we can use these two terms exchangeably. So to calculate this guy, right, if we follow the definition, we can definitely look at what is the joint density function for both x and z, and divided by the marginal density function, right? And now once you calculate this, you just need to take a look at what's the value for x taking 3, right? Does it make sense? This is one way of doing this, is just to follow the very standard definition. Right? So, but probably we can directly, alternatively, right? Probably we can directly calculate this conditional density function. Can we? We can think about that, right? Can we directly compute this conditional density function? What's the probability of z taking different values, condition on x taking 3? Can we do this? Yeah, let's try to do some analysis, right? So first, what are the possible values that they can take? Remember, Z is a summation of the points of two dice. Yeah, I mean, you're absolutely right, but let's just postpone a little bit. Right? Let us do not consider the constraint, like x equals 3, right? Let's just think that, okay, we define Z as the sum of the two dice, right? So we know that each die will have at least 1 point, right? At most 6 points. So Z, in theory, can take the value from 2 to 12, right? Does that make sense? Right? But now, let us look at what is the conditional probability, right? If Z given X has already taken the value 3, right? This is the probability that Z given X equals to 3, right? So let us list the possibility, right? So is it possible that when X takes 3 and Z takes 2? If so, what is the probability? It's not possible. Why? Yes, right? So this is something we should be really aware. Remember, Z is the summation of X and Y, right? X, Y are both points you see from the two dice, right? So one dice has already, the first die has already showing that, okay, it's point 3. So Z cannot take 2, right? So that means if Z takes 2, this probability must be 0. Right? Is it possible that Z takes 3? No. Why? Yes, exactly, right? If Z also takes 3, that means the second die will show you 0.0, which is not possible. So this is not possible to take the probability that Z is 3 given X equals to 3 is 0, right? Is it possible for Z to take 4? Yes, right? Z takes 4 implying that Y will take 1, right? So what's the probability that Z takes 4 conditional on X takes 3? Yes, 1/6, right? Remember, this is like equal chance die, right? So you see the chance you see every point is the same. So conditional X equals to 3, Z equals to 4, meaning that you actually say Y equals 1, right? The chance for this is just 1/6. Question? Everyone's good? Okay. So how about 5? What's the probability that they takes 5 conditional on that X takes 3? It's also 1/6, right? The reason is simple. That means Y will take 2. It has the equal chance, right? So it's still 1/6. So we can continue doing that, right? We say Z can take 6, we can take 7, we can take 8, Z can take 9, right? The correspondingly, conditional X equals to 3, it means Y will take 3, 4, 5, 6. And the probability will be what? What's the probability that Z takes 6, condition on X takes 3. They're all 1, 6, right? Because these different values of Z taking all just implying Y takes different points, right? 1, 2, 3, 4, 5, 6. And those probabilities are all 1 over 6 because those are equally rolling die, right? So they're all 1 over 6. But we have not yet exhausted all possible values about Z, right? So how about the probability Z takes 10, given X takes 3? Yeah, I saw someone show this, right? Y is 0. Yes, exactly right. So if Z takes 7, that basically means Y will take 7 because X takes 3, right? And it is not possible because the biggest point you have seen from a die is just 6. So that basically means the probability here is 0. And similarly, Z cannot take 11 because that means the Y will take 8. So this probability is 0 and 12, 0, right? So now we have worked out the conditional probability density function of Z given or conditional on X equals to 3. Does it make sense? Any question? Okay, the last step is just quite mechanical, right? You're gonna just leverage this conditional density function to calculate the expectation, which we can just take non-zero entries, right? Because for Z taking 2, 3, 10, 11, 12, the conditional probabilities are all 0. So we don't need to include them. So that will be, and for the remaining ones, like for the remaining possible choices of Z, the conditional density function always takes the value of 6, right? 1 over 6. So it is 1 over 6 and summation of 4 plus 5 plus 6, 7, 8, 9. So basically, basically the result is just you average through from 4 to 9. Any question? Everyone's good? Okay. So, oops. Yeah. Okay. So let's take a 5 minutes break and then continue. Hey, so let us continue. So now we're going to start talking about additional concepts, which are called covariance, correlations, and bivariate Gaussians. So we have discussed about if you look at two random variables together, x and y, right? And if you want to know their joint information, what they can represent, we usually seek for the joint probability density functions, right? But in many cases, this kind of joint density functions are not available or very, very hard to compute. So then how to characterize the relationship between two random variables, right? Sometimes we have to step back and seek for some kind of compromise. So covariance and correlation, these kind of concepts are built upon this kind of idea, right? Okay. So as we previously discussed, right? When we have two random variables, x and y, described jointly, we can take the expectation of the function of both, right? So how can we do that? Suppose we have a discrete random variables, meaning that x, y are both discrete random variables. That means their joint PDF is just the probability that x take a particular value of AI and y takes a particular value of bj. Right? So if we want to calculate a function, we want to calculate the expectation for a function of x and y. We just do this integration with the function. So this is an extension of the single variable case. So if we could recall, suppose I know my probability density function for a single random variable x, which we denote by f of x. Now, I want to look at the expectation of some function of x. How should we do this? Did anyone recall? Any thought? Like I know this f of x is my probability density function for x, right? Of course, if I want to calculate the expectation of x, I'm going to do some integration of x times the PDF of x, right? So now, what if I want to calculate the expectation of a function of x, say g of x? How do we calculate such expectation? Yes, exactly, right? So you don't need to really look at, okay, if you don't need to assume this guy is a third random variable z and what's the PDF for z. That will be make things much harder, right? So instead, if you want to compute the expectation of g of x, you're doing similar integration, but now you're going to replace x by g of x. You times g of x, you multiply g of x with f of x, then do integration. Then that's it. Okay. So this applies to any function, any transformation of a random variable. If you want to calculate what's the expectation after the transform. So now, if we extend it to two variables, right? So suppose now I have a function g of two variables, x and y. If I want to calculate the expectation of g of x, y, how should I do this? Any thought? Any guess? Yeah, we're kind of doing same thing, right? The only difference is that now I'm gonna multiply g with the joint density function for x and y, right? So now, because g is a function of both x and y, right? So now if we want to leverage the density function, we should leverage the joint density of x and y, right? That's the only difference. So you can still do the integration. Now you multiply g xy with the joint density of xy. Now you're gonna do the double integration, or dx and dy. So that's how we compute the expectation of a function of two random variables. Question? Does it look good? Okay, so now if we look at the formula given here again, it will be natural. So first, if x and y are discrete random variables, we know this f, right? This joint density function is just a table, right? It's just a discrete function at which you're going to take different pairs of x and y values. You're going to have different probability density function value. So your integration becomes a summation, like double integration becomes double summation. Right? So if we have continuous random variables, x and y, now it becomes double integration because f, the joint density here, is continuous. Any question? Again, let me emphasize again, this is just a straightforward extension from a single variable case to a bi-variable case, right? So single variable, for single random variable, if you want to calculate the expectation of a function of that variable, you're going to multiply this function g with the probability density function for that variable x, then do the integration, right? That's how we calculate the expectation of g of x. So now, if we extend this case to the bivariate case, right, where your g is now a function of two variables, x and y, and then the calculation would involve multiplying g with the joint density function of both x and y, because now g is a function of two variables rather than a single variable. Question? Okay. So now let us use this result, right? Let us consider a very special form, namely g of x, y is just a linear combination of x, y. Yeah. Here, we're going to use this definition to recover the result of the linearity of expectation. Right? So let gxy equals to rx plus sy, right? Of course, r and s are two constant, right? They are not random variables. R could be 2, s could be 0.5, whatever, right? It's not random variable. So then let's see if we want to calculate the expectation of gxy, what will it be look like, right? So if x, y are discrete random variables, right? So say according to the definition, the expectation is a double summation, right? Double summation over every possible values x, y can take, every possible pairs x, y can take. And then you evaluate g at these two values, which is r times ai plus s plus times bj, and times the joint density function, which is fxy equals to ai, y equals to bj, right? Then through some arrangement and summation, you can get this expectation is simply r times expectation of x plus s times expectation y. So you see the linearity. The expectation of a linear combination of x, y is a linear combination of the expectation of x and the expectation of y. Question regarding the conclusion. Does this conclusion look clear to everyone? Now we would like to see why, right? How do we derive this, right? We're going to leverage the marginalization, the joint density, those definitions we have discussed, right? So let's start with the definition. Our G function is just a linear combination of x, y, r times x, s times y, right? And according to we just discussed, this expectation would be, you're going to integrate this G function, right? This G function with the joint density function, and then do dx, dy. So remember, this is a double integration, right? I mean, if x, y are discrete, you're going to replace the integration with the summation. Everyone's good? Everyone feels good about this, right? So then we know that g of xy is simply rx plus sy, right? So just to do some substitution, which is rx plus sy and f xy dx dy, right? So now we just need to do some kind of arrangement, which we have practiced a lot in calculus 1 and calculus 2, right? So the summation, the integration of summation is a summation of integration, right? So we can just use associative law. So we can decompose this as a summation of rx, integration of rx times f xy dx dy, right? And second term would be sy times f xy dx dy. Do we agree? Question? Right? So from here to here, we just use a distributive law, right? You just multiply fxy with each term, and then you kind of like doing integration first and do the summation, right? Right. So then let's take a look at each summon. So the first one, we can first try to do the integration y, right? So because x will be viewed as constant to y, so you can take x outside, right? So what you need to do is that, okay, I'm gonna first integrate xy or dy here, and then do dx. Does it make sense? So now I want to ask, what does this integration of f xy with respect to y mean? Yes, right? So you integrate the joint density only with y, that means you're going to marginalize out y, right? So the remaining will be the density function, marginal density function for x, right? So now if we take a look the whole term, right? So it is Rx times Fx, right? This is the marginal density for x, d of x. Again, R is a constant, so we can move it outside, right? Right. So what does this guy mean? Yeah, this is expectation of x. So now we get our first term is actually R times the expectation of x. Yeah, let's take a look at another term, right? The second term, again, we're gonna first integrate out x, right? So we first do fxy and d of x. Then in outer level, we do d of y. So what does this integration of f with respect to x do? And what's this? Yes, exactly, right? That's the definition of a marginal density, right? So if you integrate f of xy only with y, you're gonna have x remain, right? So the remaining will be the marginal density function for x. So we got this one will be the marginal density. Oh, sorry, marginal. The remaining will be marginal density for y, right? Because you marginalize out x. Right? So the remaining variable is y. So the remaining is the marginal density function for y, right? And then combine with the outer integration, right? Sy times d of y. S is a constant, so we can move it out of the integration. So it is S times y marginal density of y dy. So what does this integration mean? Any thought? Yes, expectation y, right? So now we have a second term, which is the S times expectation y. We know that we add them together. Okay. So now this gives the rigorous proof showing the linearity of the expectation, right? So previously we mentioned that we treated as a valid conclusion, we just use it, right? But now with the concept of the joint density function, marginal density function, and with those definition, we can directly prove that the linear combination of any two random variables, its expectation is the linear combination of their respective expectations. Question? Everyone feels good? Right. This is a very, very useful and wide used conclusion. Like in the future, if you have like in-depth study about information theory, electrical engineering, machine learning, data science, artificial intelligence, you're gonna constantly use this conclusion. So hope everyone really like this, know this group. Okay. So next, it comes to our definition of the covariance. So why do we revisit the linearity of expectation? Because it directly gives our two forms of the definition of the covariance function and covariance. So the classical definition of the covariance is as follows. The covariance is defined over two variables, and it is calculated as an expectation of a function of these two variables. This function g is x subtracted by the expectation of x times y subtracted by the expectation of y. You see that, right? So the covariance function essentially, no, sorry, it's not covariance function, it's a covariance. Essentially, is just an expectation of a function of two variables. But this function has this particular form, x minus the expectation of x times y minus the expectation of y. Okay. So an interesting observation is that if you replace y with x, meaning that you just calculate the covariance between x and x, then the covariance is reduced to the variance of x. Okay. So we can take a look, right? So this is the definition, right? The covariance is defined as expectation of this function, x times x minus ex times y minus ey, right? So now you replace y by x. That means the second parenthesis inside will become x minus e of x, right? Now, you know you're multiplying the same thing for twice. Now, that means we're gonna take the square of x minus ex. This is the definition of the variance of x. Question? Everyone feels comfortable? Okay, so what does covariance mean, right? So intuitively, we can view covariance represents whether the two variables is varying along the same direction. Like you can imagine, what happens if this covariance is bigger than 0? Okay. So it will be the case that, okay, most of the cases, suppose x, y are just mapping some random experiments, right? So your observation of x, when it is bigger than the expectation, then y should be bigger than y's expectation as well, right? Or if x is less than the expectation, then y should be less than expectation as well. Then when you multiply them together, it is positive, right? It's like, okay, suppose this line represents the axis where y takes value. This line represents axis y takes values. So those are the expectation, right? Yeah, y, right? So the positive covariance basically means that in most cases, it's like when you take y here, then when you take x value, we observe x is here, then y will be observed on the right-hand side of its own expectation as well. Okay. When x takes some value below the expectation, the y should be, in most cases, taking the value below the expectation y as well. That will lead to the overall covariance to be positive. On the other hand, if you got a negative covariance, that basically indicates that in many cases, or in most cases, when x appears to bigger than the expectation, and then y will take a some value less than expectation. Or when x takes some value less than its expectation, y will take some value bigger than its own expectation. That's why it's called covariance, right? If you vary along the same direction, then your covariance is positive. If you vary on average in the opposite direction, then the covariance is negative. Question? Okay, let's stop here today and see you on Thursday.